This is Person, and he's about to finish this major job you've been working on, which is the James Webb Space Telescope. Sunshield for the James Webb Space Telescope. The James Webb Space Telescope is about to launch, and this is a really big deal that people from all over the science community have been waiting on for years. By the time you watch this video, it may have already launched, or it may have been in operation for decades. It doesn't really matter, because today we are going to talk to a very special person and we're gonna learn a lot about the James Webb Space Telescope. The James Webb Space Telescope is too big to fit into any rocket payload fairing, so in order to get it to space, it has to be folded up and launched in this more compact configuration. After launch, it's designed to unfold like origami in what I see as a series of precisely choreographed engineering miracles. Not only do you have to make sure all this stuff works, but it has to happen after the incredibly violent vibration environment of a rocket launch. Projects like the James Webb Space Telescope, or the JWST as it's known, take so long to make and are in operation for so long, it's incredible. You just saw my dad, and I would be fascinated with the James Webb Space Telescope whether or not Dad worked on it or not, but the fact that he did makes it we're gonna explore exactly what Dad did on the Sunshield, because it's really cool and there's a lot to learn there. But first, I want to learn about what the James Webb Space Telescope is, how it works, all the important things, and we're gonna do that by talking to a very special individual. A number of years ago, back in 2017, I had an incredible honor. I was invited to Goddard Space Flight Center, and I had the opportunity to speak with an incredibly important person working on the project. Dr. John Mather. Before we start this conversation, I want to explain its importance to you. If you could pick any human in all of history to explain the James Webb Space Telescope to you, you would pick Dr. John Mather. First of all, he's an astrophysicist and a cosmologist, and he actually won the Nobel Prize for Physics along with George Smoot for his work on the Cosmic Background Explorer satellite. What I'm trying to say is he understands the night sky like no other. And astronomers have been looking for the center of the expanding universe for a long time, and there is no sign of it. Imagine an infinite universe that is expanding into itself infinitely, without boundary, without a center, without an edge. The second reason you'd want to listen to Dr. Mather talk about this is because he is the senior project scientist over the James Webb Space Telescope. And what that means is he represents the interest of science to the project managers over the project. And given the fact that he knows all this stuff and the whole project is about science, you can imagine how important that means his perspective is. Not only are we speaking to a brilliant mind who knows many, many things, he's also very kind. For example, when I'm doing the interview, which isn't the best execution of an interview I've ever done, I'm trying to film him in the side room of a little conference center. My camera kept overheating, and he was very patient with me, as I hope you will be too. It's just really, really simple. We're talking about the most complex thing the humans have ever built in a very simple way. And I'll interrupt throughout our little interview here, and we'll have some little simple drawing conversations. Let's go talk to one of the many brilliant minds working on the James Webb Space Telescope, and let's try to get smarter every day. Alright, so this is Dr. John Mather. Am I allowed to say Nobel laureate? Yes. Alright. Yes. Indeed. Do you mind talking to me about James Webb for a second? I'm happy to do that. Let's go ahead and get comfortable. So what I'm interested in doing, with your permission, is creating a video series about how the James Webb Space Telescope works. James Webb Space Telescope works. I'm one of the many. Here's the telescope, and you can see that it's not like anybody else's telescope. It's not like the little tube that Galileo looked through. It's not like the Hubble Space Telescope. It is way out there in space. It looks more like a solar energy concentrator. And it has this huge hexagonal mirror made out of 18 smaller hexagons to collect the starlight, or the galaxy light, that comes from over here. It bounces off a little convex mirror up here and back down into this black area, which is the beginning of the instrument package. It's a Casagrandian. These two parts make it a Casagrande. There's a third big mirror that you can't see that makes it called a 3-mirror anastigmat telescope, which is better. Say that one more time. 3-mirror anastigmat. I'll have to go look at that. It means that it gives a good image over a much larger piece of sky. Got it. And so we really care about that because we want a really good image, and we have a big camera. So I did have to look that up. 3-mirror anastigmat. Basically, it means that light gets bounced off of mirrors 3 times before it gets to the instruments or sensors that are taking the picture. Each of those mirror bounces is for a very specific reason. The big mirror essentially is like a big bucket. It collects all the light as it's traveling through space, and then they focus that down. They want it as big of a mirror as possible because that means they can get more light. A bigger bucket. So all this light reflects off that big, concave mirror and is focused down onto the little secondary mirror in front of it.
Think about it.
That is so much more light hitting that little mirror than if the little mirror was just looking out into space by itself. All that light then goes deep into the telescope and is bounced off one more mirror, and then it goes to what's called the fine steering mirror. This mirror compensates for the movement of the spacecraft and kind of works like image stabilization, and back here in the back on all these optics, that's where all the astigmatism is taken out of the image. 3-mirror anastigmat, but there's a 4th mirror in there to work like image stabilization.
Got it.
The hardest thing for us to build was this giant mirror because it's made out of 18 pieces, and they all have to be adjusted to the right place after we get upstairs into space. So each of them is made out of beryllium, which is very light and very stiff and holds its shape when it's cold. That was our hardest thing, to learn how to make them ultra-light, because each of these hexagons is something you'd be able to lift with your hands if we'd allow you to do it. So they're really thin material and really, really accurate. Behind the telescope mirror is the instrument package, which has the cameras and spectrometers, and we had to invent some things for that, too. We needed much better detectors. The detectors are made of 2 flavors, one called mercury-ricadmium telluride, and one is called arsenic-doped silicon. The combination of those 2 things give us the sensitivity to the whole wavelength range that we wanted to study. And that didn't exist before? Well, they existed, but they weren't good enough. They weren't sensitive enough, and they weren't big enough.
Gotcha.
So we really had to push on that. Other things that are obviously difficult is, how are you going to make this big thing? So what I'm pointing at here is the sunshield. So it's made out of 5 layers of thin plastic coated with metal.
Captain.
So the sunshine comes up from this side, and it's all reflected away. So only a little tiny bit of heat gets through to this side, because we want the telescope to be cold and also very stable. Gets through to this side because we want the telescope to be cold and also very stable. Basically the telescope will be flown in such a way that the sun's rays are always hitting the bottom or the instrument side of the sunshield and leaving the mirrors in the shadow. Just like on Earth when we only see the stars when our side of the planet isn't facing the sun, which we call nighttime. Well, this big sunshield, the Webb, can create its own continual night for the telescope. One side of the telescope is always in the dark and the other side is seeing light, which is a really interesting way to do this because typically you have to do thermal management systems to keep everything at the right temperature. But when you keep the optics cold you don't have to worry about temperature fluctuations. So you can set it the way it needs to be and you can let it do its thing. This is a fascinating engineering problem and we'll talk about this more in a future episode. Things that are more ordinary we still have to think about on the warm side of the sunshield is the spacecraft box that contains all the spacecraft electronics, the power supplies, the rocket engines, the fuel tanks, the transmitters and receivers and the computers, everything that it takes to run the observatory.
It's on this side.
Is that how you also position the spacecraft? Where are the reaction wheels? We have reaction wheels in here that are used to point the spacecraft in the right direction, and we have rocket jets which are used for 2 things. One is to maintain the orbit because it's an unstable orbit and the other is once in a while to unload the reaction wheels because the reaction wheels collect angular momentum, and where do you get the angular momentum? You get it from sunshine, which pushes on the telescope and isn't totally balanced. So the combination of those 2 things means you have to use fuel, and that's the thing that sets the lifetime of the observatory. Okay, that was a lot, but we can understand it. Check this out. Reaction wheels are amazing and I did a whole video on them years ago that goes into depth, but it's basically a way of orienting or pointing the spacecraft without using a rocket just like cats do. You should probably go back and watch that one too. One way I like to think about reaction wheels is motocross. This video from way back shows it pretty well. So a motocross racer goes flying up into the air and they're briefly kind of weightless like a spacecraft, but riders are able to control whether the nose of the bike goes up or down by braking or accelerating. If they accelerate the back wheel the nose goes up because the reaction torque spins the bike in the opposite direction of the wheel. And if they want to pull the nose down then they hit the brakes and all the torque of slowing down the wheel is redirected into the bike and it tilts down. Basically it's the same idea on a space telescope, but instead of attaching motorcycles to it to turn it in different ways they have little electric flywheels that are always spinning, and if they accelerate them or decelerate them the angular momentum is transferred to the telescope and they can spin and point the spacecraft very precisely in all sorts of directions using a combination of reaction wheels oriented in different directions. The other thing that's fascinating about the James Webb Space Telescope is we're trying to keep it oriented in a very specific direction, but we're getting all this pressure from the sun. It's called solar radiation pressure. Basically as light and radiation from the sun hit the telescope they actually apply pressure to it, not unlike a sail. It's a really small amount of pressure, like 1/1000th of a gram on a square meter of spacecraft, but if you think about it, if you're in 0 g in the vacuum of space, a small force can offset everything and you have to account for that. It's a really big deal. So way back in the back of it, where you can't see it in this black section behind the mirror, is a huge box full of instrumentation, and the instruments include cameras and spectrometers to cover the entire wavelength that we can see, which ranges from 0.6 microns, which you can see with your eye, out to 28 microns wavelength, which you definitely cannot. So he said the spectrum ranges from 0.6 microns to 28 microns. That's a measure of the wavelength of the light they'll be able to detect. This means the telescope will just be able to see the red portion of visible light, but it will the red portion of visible light, but it will look deep into the infrared spectrum. Obviously, there must be some huge advantage to focusing so much on the infrared spectrum, and he's about to talk about that in a little bit. So we also have spectrometers that spread out the starlight into the rainbow of colors, and to find all the measures of what's going on inside the object. So the first thing you want to know is, what's it made out of? So then you look at the what's called spectrum lines. So the spectrum lines come from different chemical elements and molecules. And just as you see when you look at the fireworks on July 4th here, each different color comes from a particular chemical element or molecule. But it's different, though, because you actually have shifting, right? Yes. How do you know that you're detecting the correct elements if you're redshifted? You actually have to detect a pattern. If you only see one line, one spectrum line, you cannot be 100% sure what it's making. So you really need to find two or more if you really want to be sure you're seeing what you think you're seeing. But then this accounts for the fact that sometimes the objects coming toward us are going away from us or participating in the expansion of the universe as a whole, which can change the wavelength rather substantially. A thing that's going away from us has the wavelengths of light that we receive increased. So the fractional increase is called the redshift. So it can go from 0 or even minus if the thing is coming toward us to large numbers. And so far, the farthest thing we've seen with a telescope has a redshift of 11, which means the fractional shift is 11. Means the wavelength that we get is 12 times what it was when it started. For instance, the Lyman alpha line at 0.12 microns wavelength, by the time we get it, it's at 1.44. So this is why infrared is so important, because everything has shifted that direction. Right. So for studying the distant universe where the expansion has stretched out all the wavelengths, you definitely have to have an infrared telescope to study the light that started out as ultraviolet. So quick question. So if you've seen a shift of 11 times, does that mean that you have a sensor on board that will sense beyond 11 times? Yes. Okay. So our telescope, well, it depends on what wavelength you started with. But if you started with that particular Lyman alpha line from hydrogen, at a redshift of 11, it's 12 times the original wavelength. There is 1.44 microns.
Got it.
But suppose the universe has got things even further away, so that we see even more expansion since that time. We're set up to see, and we think we might see, objects out to a redshift of 20 or 30. Are you excited about that? Yes. Nobody's ever seen them. They are predicted. We are fairly confident of some of those predictions. But this is a good time to talk about redshift. You've experienced this in a way with a siren in the Doppler effect. As an ambulance or siren comes towards you, you experience a higher tone. But as it passes you and moves away, that tone gets lower. The sound waves from the siren are compressed against each other as it comes near you. So it appears to your ears as if it's a higher frequency. And the sound waves seem to be expanded as it moves away from you. And your ears perceive it as a lower frequency. The same thing happens with light. So as light from a star that is moving away from us reaches us, the way we see that light is an expanded version of that light. Like the tone from the siren drops, the frequency from the light appears to drop, and it moves from the visible spectrum down into the infrared spectrum. So if we didn't look into the infrared range, we couldn't see light that started out as visible light on things that are moving away from us. This is the redshift. And in a universe that's ever expanding, as visible light on things that are moving away from us. This is the red shift, and in a universe that's ever expanding, many of the objects we're looking at and looking for will be moving away from us. So looking in that lower infrared spectrum is super important. So this is a giant tripod. There's 3 legs with hinge points here, 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 and this leg folds in half, and here's a hinge point. So to get this ready for launch, we pull this one out sideways so you can pull the mirror up here and the legs actually fold around behind the observatory. Wow. So it just fits. You had a glimmer in your eye when you said that. That's a big deal. Yeah, it's a big deal. It's one of many things that have to work when you launch. Of course, everything is folded up for launch. Everything has to unfold and do the right thing out there. So of course, the big question everyone has is, are you sure it's going to work? And the answer is, of course, you can't be sure. But we are doing what we should be doing to make sure. So what do you do? Well, number 1. You have 2 of everything when you possibly can. So you get 2 shots when you need them. You rehearse everything. You practice and practice and practice. And you have grouchy people come to tell you when you're not doing it right. That's really important because we hate doing it wrong even if we don't like being told. What are those people? The quality assurance officers. Those are review panels. We get peer reviews. We get senior engineers that have done something related before and that have a good instinct about these things. We made a pathfinder for the telescope with the carbon fiber framework, and we put on 2 of the mirrors, or even finally 3. And my camera overheated again. At this point, I'm starting to get embarrassed, but don't worry about it. This gives us an opportunity as the camera cools off to get distracted by cool things at NASA. This interview took place at NASA's Goddard Space Flight Center in Greenbelt, Maryland, which is where they've been controlling the Hubble Space Telescope for the last several decades. I spoke to the Hubble operations manager and got to see the actual control room. That's a topic for another day, but they do all kinds of awesome stuff here at Goddard. So you're going to make this space telescope and you're going to put it up into space. You don't want the first time it sees a vacuum or near absolute zero on the sensor side. You don't want that to happen for the first time in space. So you got to try to simulate that on Earth. How do you do these incredibly physically challenging things here on 1 atmosphere on the surface of Earth? The answer is a huge thermal vacuum that was built at Goddard back in the 1960s, and it's incredible. So basically a large vacuum, and they pump liquid nitrogen into it to make it cold.
Make it cold.
Make it simulate the environment of space. It's made to keep pressure out instead of take pressure or contain pressure. All designed on paper, you know, back in the 60s. You think about it like that.
It's all analog.
Okay, so we're on the top floor now. We are walking towards the top of the thermal vacuum chamber.
That's cool.
So do they actually put James Webb in there? Some of the components before the assembly, they would take some of the larger components and put in this one. Then we have a bunch of smaller ones over there. They test everything all the way down to the nuts and bolts. These are also thermal vacuum chambers. These also are just smaller scale.
Oh, this is for component level stuff? Correct. Gotcha. Nuts and bolts. Nuts and bolts.
And smaller assembly parts.
Oh, that's cool.
They've got the hydraulic diagram. Or just smaller scale.
Oh, this is for component level stuff. Correct. Gotcha. Nuts and bolts. Nuts and bolts.
And smaller assembly parts.
Oh, that's cool.
They've got the hydraulic diagram integrated to the valves.
That's pretty neat.
What do you think that was printed?
Oh wow. My bad.
Got a little bit distracted. The next thing they want to test for are the launch forces that happen on the rocket. They have a huge centrifuge at Goddard, and they can place instruments on that and simulate the G-forces that the telescope will see during launch.
It's pretty awesome.
And then there's the vibrations that will happen during launch. Okay, this is the shaker table. So the Ariane is going to shake violently. What you have to do is you have to make sure that the telescope isn't going to break during launch. So here at Goddard Space Center, check it out. It's a really cool area here. This is the way they test that. They'll put the telescope here, they'll mount it in position, and then they'll shake it violently to make sure that nothing falls apart, nothing breaks. Here's some B-roll footage of them doing that, the vibration testing. You can see the telescope shaking. Okay, I'm in a really neat spot right now. This is the tent that they move James Webb around with. It's like a portable clean room. And this is the sound chamber, where they're going to acoustically load the thing. What they're doing here is simulating the roar of the rockets, which can get up over 140 decibels. It can be very destructive. So they've got this big chamber with speakers in it with a massive subwoofer and other speakers to blast it with sound. That's a subwoofer up top? This is the largest subwoofer in the country, as far as I know. And so if you really want to drop the bass, this is where you come. The cool thing about a sound chamber is that the sound is different at different parts in the chamber, because you get reflections and echoes off the wall. For example, if I have a sound wave going across and bouncing off the wall, you might get constructive interference, meaning you get a louder sound at different points, and you might get a quieter spot. So in order to test that, you can see they have microphones hanging at different points in the chamber. Wow! I'm going to get back behind this, because I don't want to interfere with what they're doing. These people are moving this tent by hand. And the way they're doing that is on an air bearing. They've got compressed air pumped to the feet of the tent and a really flat surface floor. And they're able to move the whole thing by hand. Here's a couple of really cool shots where you can see people moving the entire space telescope by hand within the portable cleanroom on a cushion of air. Can you imagine what they're thinking?
This is so rad.
So my camera's overheating. Is that a problem on the telescope? The observatory doesn't overheat, because it's facing outer space. The whole telescope is protected from the sun, from the Earth, and from the moon all the time by this giant sun shield. And we chose the orbit especially so we could do that. The Lagrange point 2 orbit that we choose is actually the only place you can go where the single-sided umbrella that we build can protect the observatory completely from all of those things at the same time. Lagrange points are special points in space where when you have two orbital bodies interacting with each other, there's these little special spots where things can kind of just balance. They're right in the sweet spot where they're being pulled in two different directions at the same time, and they just kind of hover there. Lagrange points are fascinating. There are 5 Lagrangian points for any combination of two orbital bodies.